let's now consider the case, like extend the idea. So the problem is that maybe we don't have a binary function. We still have a binary classification, but the data points that are going inside the perceptron are not necessarily binary, right? So it means it could be some classification problem like this, right? Any point inside the blue area is, for example, classified as 1. Any point outside the blue area is classified as 0, right? This is a problem that you want to solve. Can you solve it using a perceptron? Can you do it? Yeah, a single perceptron. Can you do it? No, you cannot do it by a single perceptron because there is no single line. Any line that you draw, there are both white and blue points on both on one side at least, right? So you cannot draw one line where the whole blue region is on one side and the white region is on the other side, right? That guy does not exist, but you can do it by multiple perceptrons again. How you can do it? Well, maybe I draw 3 perceptrons like what we did before. Then those 3 perceptrons are going to just look at this region, right, in between the 2 lines. Everybody's cool? So I use 3 perceptrons. It's going to specify this region. Any points in between is going to be classified as 1. Any point outside is going to be classified as 0, right? So this guy has a still error. I can consider also 3 other perceptrons to classify this problem. Any point in between of these 2 lines is classified as 1. Any point outside is classified as 0. Now, if I intersect the 2 regions, this is going to solve my problem, right? So if I intersect this guy with this guy, I'm going to end up with this, right? And this means any point inside this region is exactly the blue region, is going to be classified as 1. Anything outside is classified as 0, right? So if I have 3 plus 3 plus 1 last guy, 7 different perceptrons, I can solve this problem, right? Everybody's clear? You can actually do it with less number of perceptrons, right? So you can think about it. You can obviously do it with 5 different perceptrons as well, right? The first one is each one is taking 1 edge, right? Just this classification, this other classification, and so on. And then you intersect all of them, right? Then you need 5. So you can actually optimize the number of perceptrons that you want. But at the end of the day, if you have enough number of perceptrons, then you can definitely solve this problem, right? So this is what we can say. We can say that if we have enough number of perceptrons, we can always solve a binary classification problem. Now, maybe I can solve any binary classification problem, but does it guarantee that I can solve any classification problem? Like my classes are not binary. They are, for example, ternary, right? I have 3 classes, not 0, 1, 0, 1, 2, right? Or even more. Does it guarantee that I can still solve it using perceptrons? Well, we talked about this before. Any other classification problem that you have, you can write it down as a sequence of binary classifications, right? So you would say, okay, a binary classification between class dog and the other class which contains cat or car, right? If it's classified as dog, then the problem is over. If it's not classified as dog, then it's either cat or car. I do another binary classification. I find out whether it's a cat or car, right? So moral of the story here is that if you have any classification problem, and it does not matter whether you have a binary classification or you have a multi-class classification, at the end of the day, you're able to solve it using enough number of perceptrons. Everybody's cool? Questions? One question. If you have this classification problem, you have a circle, everything inside circle is 1, everything outside is 0. How many perceptrons you need? Infinite number of perceptrons, right? You cannot exactly solve it with finite number of perceptrons, but if you have infinite number of perceptrons, then you can just draw all the tangent lines around the circle, right? And then inside is 1, outside is 0, right? So maybe enough number of perceptrons is huge, but at the end of the day, if you have that much, then you can solve the problem, right? Everybody's clear? Questions? No question? Okay, great. So if you got no question, then let's go for the last part of the question we had. So we said if we have any classification problem, we can collect enough number of perceptrons, and then we can solve that problem, right? That is possible. But what if I have, instead of classification problem, a problem that the output, the label that I have inside my data set, is not coming from a class. It's not, finite number of distinct classes. Maybe this is a real number, right? Do you know what kind of problem is that? So you want to find out a function which takes a bunch of inputs and then computes something real values for you at the output. That is? Yes, go ahead. That is a regression problem, right? If your model is linear, it is going to be a linear regression. If your model is not linear, then it's not a linear regression, right? So that is what we call it the problem of regression. It means that the output, the label y that you have is real valued, is a continuous number. And again, yes, if you have enough number of perceptrons, you can solve that problem as well. Everybody's cool? So let me show you how you can solve it. It's not complicated. It's actually very easy to see that you can solve that problem as well. So let's say that I have this function, right? So I have this particular function g. I want to learn it, right? So it means that at the end of the day, I want to design a model which is able to exactly match this function, right? So I need to have a model which is capable of getting very close to this behavior, right? Now, what I'm going to do, I am going to start with this particular function, which is a step function. I want to see if I can connect a bunch of perceptrons together, such that when I give an input to this network of perceptrons, this neural network, I'm going to see this pulse at the output. Can I do that? Do you think I can do this? Let's first think about the perceptron here. How many inputs do I have? How many parameters I have? What is the dimension of x here in this diagram here? It's? What is the dimension of x? Come on, please. It's 1, right? X in this diagram is 1. I do know x could be very large. I'm talking about this guy. You see it? X is 1 dimensional. It's a number, right? It goes inside this pulse function. If x is between alpha and beta, then it's going to give me as the output 1. If it is anything else, it's going to give me 0, right? It's still a classification problem, right? Basically. Everybody's cool? And I can solve this using a perceptron. So my perceptron is going to look like this. It's going to get a single x. It's going to multiply it with w. It adds up the bias, and then it's going to check the sign. If the sign is positive, the output is 1. If the sign is negative, the output is 0. Everybody's cool? Yes? So this is the perceptron that I have. Now the question is that, can I collect a bunch of these perceptrons and I make this function? Can I do that? I can do it. Again, I can do it by 3 perceptrons. Let's look at the first perceptron. This is my first perceptron. I put w to be 1, the bias to be minus alpha. Okay? What's going to happen? X goes in, multiplied by 1, going to remain x, minus alpha, right? You're going to check the sign of x minus alpha, right? If it's positive, you're going to give 1. If it's negative, you're going to give 0, right? So x minus alpha, after alpha, if you are taking any x more than alpha, x minus alpha is, everybody? It's positive. The output of the perceptron is going to be 1, right? Anything less than alpha, x minus alpha is negative, the output is 0, right? Now, if you choose w to be minus 1 and the bias to be beta, then the term you compute by your perceptron is going to be minus x plus beta, right? When x is smaller than beta, this is positive, right? So here, this guy is going to be 1. When it's more than beta, that term is negative, so here is going to be 0, right? And if you get the output of these 2 different perceptrons, and you intersect them, what you're going to get? You're going to get exactly this pulse, right? Everybody's cool? So what I am doing, I get my x. I'm going to check it with alpha, the first point on the first boundary of the pulse. I also check it with beta, right? And then I AND them. So this guy is going to give me 1 when my x is in between. It's going to give me 0 when x is out of the interval, right? Everybody's cool? So I can actually learn this pulse using 3 perceptrons, right? But we are talking about a more general function, right? So I can actually represent this pulse using these 3 different perceptrons. The first guy is checking the first boundary alpha. The second perceptron is checking the second boundary beta. And the last perceptron is just intersecting them. It means that I'm going to check whether we are within the interval or outside the interval, right? That is the pulse. So if I look at this whole end-to-end, the function from x to y, this is basically this pulse shown in black. Everybody's clear? OK. Now, the question was that I was not looking for the pulse. I was looking for the function gx, right? But any function that I have, I can approximate it by a sequence of pulses, right? So I can think of tiny intervals, right? And for every interval, I can get the point in the center of that interval on the function, right? And I just scale my pulse with that weight, right? With that height. Then I have the first pulse plus the second pulse and so on towards the end, right? Yeah?
We would need a different, like, ending nonlinear function instead of the sine function to scale the pulses, right?
Sorry?
Instead of this, the sine function that output is 0 or 1, we would need a different function, right?
Not necessarily. I mean, you can do it by this one. Your approximation is not necessarily exact. I mean, it's definitely not exact. But it still is a good approximation if you have very tiny intervals, right? And if your function is smooth enough, then you're going to get at some point. It's like a Riemannian integral when you compute, right? And then you just take the width of that interval to get close to 0, right? And that is a good approximation. It's not an exact representation, but it's the approximate representation. You are right. If I use another function instead of this step function, this could potentially improve the representation.
The sine function we use at the end of our perceptron, that either gives a 0 or a 1, right? But the heights of our pulses are now different.
Oh yes. After sine, you can just get that guy and multiply it with another weight, right?
Do we learn that as well?
Yes, definitely. And that is a part of your model. I'm going to show it in the next slide, okay? So everybody's cool with this representation here? So I have this very nonlinear function g, and I can collect lots of perceptrons together. Every single perceptron is going to learn one of those tiny pulses, and then I just scale those pulses to get close to the function and add them together, right? So if you want to, again, think in terms of a neural network, I could have this guy. So let's say the first point here is x0. The next one is x1. The next one is x2, and so on, right? So you are just making these tiny intervals, x0, x1, x2, x3, and so on, right? Tiny. x0 to x1 is very small. Then the thing that you are going to do, you're going to say that, OK, I have x. This x goes in. So I'm going to check x0, the first edge, x1, the second edge. I do the AND here. Just ignore this minus 1.5. It's what we got out of the previous example. I don't care about this. This is basically doing AND. Then at the output of this guy, what you're going to see, you're going to see 1 if your input x is between x0 and x1, right? And you're going to see 0 anywhere else, right? But maybe you don't want it to be 1. You want it to be something else, right? So you get this guy, and you multiply it with whatever you want, right? Another weight, right? So you do it for all the intervals. So this is the last interval, the one before the last edge, and the last edge. You're going to check this. You AND them. And now you have a lot of pulses. Every single pulse gets multiplied with its own weight. And if you add them up, you are approximating the function that you want. Again, if you just look at everything between x and y as a box, this box is approximating your function. And if you increase the number of perceptrons in this one, this is going to get more and more accurate. Yes?
So instead of minus 1.5, it should be the general. What would be the general?
No, this minus 1.5 that I put here with this 1 is going to do AND for you. So if you have, because the thing you get out of the first, these two perceptrons, you're going to get binary numbers, right? If you want to add two binary numbers, this is one possible choice you could have. Okay? But you can ignore it. Like, you can choose a lot of other ways. It's no problem. Everybody's clear?
So the weights here at the very end are just to, if you want the output to be anything but binary?
Yes, because, for example, because the first pulse that you see here is like 0 everywhere, 1 here, right? The second pulse is going to be 0 everywhere, 1 in the next interval, right? But you do not want to just draw a constant function, right? You might want to have a different function. So this guy goes up to the first level. This other guy goes to the second level, right? This is W1. This is W2, right? See that? Questions? No question? Everybody's clear? So, what I wanted to show you here is that, and I don't want you to I hope you see it intuitively, what we did here. You can actually put a bit of more math into it, and you can actually prove this, that you can learn any classifier. So if you have a classification problem, and the classification problem means that you have a weird subspace of your entire data space, entire possible points as the input, you have a weird subspace of that. There is one class for this, right? There is another weird subspace. It belongs to another class, and so on, right? And any classification problem that you have is essentially such a problem, right? And any of such problems, you can always learn it if you have enough number of perceptrons. You just need to tune them and connect them properly together, right? This is going to happen. So you can learn any classifier. You can approximate any function. So I talked about this simple scalar function with a single real valued input, real valued output. But you could have a weird function again, right? A very high dimensional function which takes a vector of thousands or maybe millions of input and takes it into thousands of outputs, right? Again, what you can do, you can just connect lots of perceptrons together, and then you can approximate this function. Maybe you do not get exactly the function itself because the function is extremely changing rapidly, but you can still approximate it, right? And the more perceptrons you have, the better going to be your approximation, right? And this is what we call it the universal approximation theorem. And I'm just presenting it here for you in an informal way. So this had been done in 80s or something. So those of you who know about Vapnik and Vladimir Vapnik, so you probably have heard of it. There are also lots of other people who try to show this. And this was one of the basic theoretical results which somehow brought this idea into attention that if you have a network of artificial neurons, probably you are capable of doing a lot of things. But the question is how you can make them do that, right? So they are having a very high capacity. They have the potential to do whatever you want. But the question is how you can make it, how you can find the weights and the connections properly so that it's going to do the job for you, right? So this is what we call it universal approximation theorem. And I am presenting it here like this for you. You don't really need to confuse yourself. I'm going to decipher what's written here. And I just want you to have this idea in mind, that neural networks are very capable of doing anything that you want. So what does it say? It says that say you have this function g. So the function g is the ground truth, the true function you want to learn. You don't know it in practice, right? But it could be a weird function, right? You have this function, and you have this epsilon. Epsilon is the amount of error that you can accept. Like you would say, okay, if I am just approximating that function up to this error, I am okay with that, right? And now, it says there exists one neural network. So this FHW, H is the hyperparameter, for example, how many neurons, how many perceptrons you want to connect together. And W are the weights, all of the weights connecting the neurons together, right? So this is one neural network. You don't really need to care about that notation. So the blue guy is the neural network. Now, what it says that you can always find such a weight, W, and such a hyperparameter H. So you can collect a lot of neurons, a lot of perceptrons, and you can connect them with right weights, such that when you give X to this neural network and you look at the output of the neural network, the difference between this guy and the true function is very small, right? And it's not talking about a random point. It says, like, you go on this function, so you have this function g, and then your neural network tries to just follow it, right? And then you look at every possible x, and you look at where it is the most difference, right? You just find the most difference. So this supremum here is basically maximum. Like, you look over all possible inputs, and you look for the maximum error. It's like some people who want to find an error, you see? Like the parents, like, I'm going to find it out, right? Open it. Like, you go over every possible data, right? Every possible data, and you see, you find the one which has the maximum error. And that guy is still smaller than epsilon, if you have enough number of perceptrons. So whatever you give me as error, you tell me that I want to just make it as close as possible. I want it to just stick to the true function. I give you, okay, no problem. Just give me 5 trillion perceptrons, and I'm going to do that for you, right? And then you would say, oh, that's too much. Maybe I can tolerate 0.01 error, right? Okay, 5 trillion reduces to 5 billion, right? But still, I need a lot of perceptron. You got the idea? Everybody's cool? So neural networks, because of this, are very powerful. And this is why they pretty much dominated the whole literature of machine learning. Because at the end of the story, in the machine learning, you want to get one model, and you want to feed it into the data, so that it's somehow approximated true function, which is describing the pattern inside the data. And what this result says, it says that the neural network are always capable of that, just when you have enough number of neurons inside them. Questions? No question? I put some paper for you on the reading list. You can take a look at that one. So these are the old papers where they try to somehow show this result. I don't want you to read the proof, but maybe it's out of curiosity. Maybe you can take a look and see what people used to do. OK. Now, if you got no question, then we are pretty much over with this kind of motivation for doing deep learning, really. And then the next thing, yes, go ahead. Yeah, sure. It should be supremum. It's like the maximum. Like the maximum. You look at every possible x, like in the one-dimensional case, x is from minus infinity to plus infinity, right? And then you find the point where you have the maximum difference between your neural network and your true function, right? So this is like the most error you can get in your approximation, right? And even that one is smaller than epsilon. Yeah. Questions? No question? OK. So if you got no question, then maybe we can officially define an artificial neuron and a neural network. So what is an artificial neuron? It's basically the perceptron with one tiny difference. Instead of having necessarily a step function at the output, you can have any function, right? This is what we call the activation function. So that is a neuron, and the way that I'm going to show it is going to be this way. So F is the activation. Everybody goes there, gets multiplied with their own weights. You could have a bias. They add up, and then they pass over this particular function F, which is activating that neuron, right? If you set that function to be a step function, you get back to perceptron, but you can choose other functions as well, right? Now, if you think about one neuron, how many weights you have here? How many learnable parameters you have? N plus 1, right? As much as inputs you have plus 1, and that plus 1 is simply the bias, right? So these are all the weights, all the W's and bias. You can tune them. So these are learnable parameters. And usually, I'm not going to show those weights when I don't need to. And then you usually get the sense that the edges are the guys which you can tune, right? Now, this is the expression between the input and output of a of a neuron. So you have the activation function. As I told you, these W's are the weights, P is the bias, and F is the activation function. Now, the activation function, you can choose it anything that you want. You can even set it to be a linear function. And if you set it to be a linear function, then you reduce to a linear model, right? But the point is that you're going to see it in your assignments that if you set it to be a linear function, then that neuron is actually not doing anything for you, right? If you want to cascade it, like if you get one neuron with linear activation and you just concatenate it with another neuron with linear activation and so on, all of it is again one giant neuron, right? So it's useless. What you do in practice, you always need F to be nonlinear. So this F must be nonlinear in practice. You can use linear choice, but if you do that, then practically you are not using that neuron really. You need to activate it because that activation is the key which makes your neural network to be able to approximate a nonlinear function. Everybody's cool? Now, there are a bunch of choices for activation. So as I told you, you usually need to just choose nonlinear function. There are a bunch of choices that you have. ReLU, rectified linear unit. That one is a quite famous one. And the main reason that we use it a lot is because this is pretty much linear, right? So when X, the input to the input after the inner product, right? So here the input is the guy here, right? The Z here. So whatever you calculated this guy, then you activate, right? So when input is positive, then you're going to pass that guy exactly at the output, to the output, right? But if it's negative, you're going to kill it, right? That is the ReLU function. This is the easiest nonlinearity you can add. But that one is enough. That simple thing is enough, right? So this is the ReLU function. You can write it down in this form, max of x and 0. You can have a sigmoid function. This is the sigmoid function. So this is, again, nonlinear function. So when you start, if you give any x into this guy, look at this expression. This exponential term, e to power minus x. Can it be negative? It cannot be negative, right? It actually cannot be even 0, right? It can only get very close to 0, right? So this term that you have is always something between 0 and 1, right? Now, if you take x to minus infinity, so you just make it as much as possible negative, what's going to happen? E to power infinity is infinity, right? So this exponent is going to explode. Then you have 1 over some explosion. It's going to be roughly 0, right? So you're going to start from 0. It goes up, 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 up. When you set x equal by 0, what's going to happen? E to power 0 is 1. Then the whole expression going to be 1 by 2 is half, right? This is the point that you cross this axis. And you keep on going up. If you increase x to infinity, then what's going to happen? E to power minus infinity is roughly 0. So it's 1 by 1, that is 1. So you start from 0, and you go 1. You cross the axis at half, and then you keep on going up towards 1, right? You never touch 1. You never touch 0, but you're roughly there, right? That is another famous or popular activation. We're going to see that one as well. You can have tanh. Again, same thing, a bounded function. And you could also have soft ReLU. And you might don't see why you can just, why you might use soft ReLU instead of ReLU, but we're going to talk about this later. This guy has derivative everywhere. The other one does not have derivative on the edge and on the left side. Okay? But this guy is actually a smooth version of the ReLU that we had. If you want to see it, assume that x is extremely large. If x is extremely large, e to power x, that one is significantly larger than 1, right? So this 1 plus e to power x, you can roughly estimate it as e to power x, right? And if you take the log of e to power x, that is x itself, right? So when x is large, that guy is roughly linear, right? Now, what if x is very, very small? If x is very small, very negative. If that guy is very negative, e to power 1 large negative number, that is roughly 0, right? So you can ignore this term, then this is log of 1, which is roughly 0. So again, you start from 0, you are pretty much there, and then when you go towards infinity, you're roughly looking at a linear function, right? So it's like a ReLU function, but a soft version of it, right? It's not edgy anymore. Everybody's cool? So that is another kind of activation function, and you can have any nonlinear function as an activation. It's going to work. These functions simply just show up to be efficient in terms of computation and complexity. Now, how we can define an artificial neural network? Well, artificial neural network is formally defined in this form. This is a network of, it's a directed graph, that connects a bunch of inputs to the outputs through a graph, right? And every node on this graph is simply an artificial neuron, right? So you got this input, x1, x2. You want to connect it to y. You can draw any directed graph. It means that you can put a lot of nodes, right? And then you can just draw edges which have directions. Like they start from one node, they go to another node, right? And if you draw that one, this guy, if you think of every single node in between to be an artificial neuron, then that guy is a neural network. Everybody's cool? So looking at this guy here, for instance, x2 is going inside, x1 and x2 are going inside the center neuron, F3, right? So they are getting multiplied to their own weights, right? A bias could add up. Then you activate it with the activation function F3. This is the output of this node, right? And then the output of this node is going to get multiplied to its own weight, and then x2 is getting again multiplied to another weight, again added up, activated, and you keep on going. You keep on going till you get to the outputs, right? This is a neural network. This is still a neural network, not like those you have in mind, but it's formally a neural network. Now, I'm going to drop this term artificial. Obviously, we don't have a real neuron. You do know that, but yeah, maybe old days people still were just indicating this is artificial, this is not real. Now, what is the depth of a neural network? You can define the depth of a neural network, the longest path you need to take to start from input and you get to the output. The longest path. Okay, let's look at this guy. What is the longest path you need? I have shown it in blue, one of the choices. That is 3, right? 1 a step, 2 a step, 3 a step, then you are at the output, right? So it's going to be 3, right? Everybody's cool? Yeah. So it's like you put x1 and x2, how much you need to wait till you see the output, right? There is a shorter way as well. I mean, you can start from x2, then you're going to be f1, f4, 2 steps, and then you are at the output, right? But even if that happens, you cannot do the computation until the other computations have arrived, right? So this is why you look at the longest path, right? And this is what we call it depth. So the depth is here 3. Everybody's cool? Great. Now, what is a deep neural network? Is a very complicated definition. Is a neural network with depth more than 2. That's it. So it's not a weird thing. It's just a neural network. When the depth is more than 2, then this is a deep neural network. Why? Because we're going to see. Questions? So this example that I had here, it's 3. It's more than 2, then this is a deep neural network, even though it doesn't look like something you imagine as a deep neural network, right? So it's not necessarily talking about the number of neurons you have there. It's just how deep it is, right? How much is the depth of the neural network? Everybody's cool? Questions? Yeah?
The depth is always determined by the longest path?
The longest path, right. Okay, now let's get a bit more practical. So typically you don't think about those weird neural networks. You think about such a thing, right? And this is what we call it a layered architecture. So a layer is basically a set of neurons which are all in the same distance from the input, right? So everybody here has distance 1, length 1. Then everybody in the next layer is in distance 2, and so on, right? So we typically design neural networks in this form, it means that we're going to get a bunch of neurons. We put them in one layer. We connect them to the previous layer, right? To the input. And then we're going to compute a bunch of outputs from them. And then we connect these guys into another layer, a bunch of other neurons, right? And so on. Okay? Now, inside your neural network, you can still, even if it's layer, you can still have weird connections. So you could have these direct connections. They're always there. You can have them full, which this is what happens in MLP. They're fully connected with our neural networks. You could have them sparse. This is what is happening inside convolutional neural networks. We're going to see that. You could have these connections which you are starting from X, and then you skip one layer, you connect it directly to another layer. This is what we call a skip connection. We're going to see it in chapter 5. This is what, for example, ResNet is working based on. You need that one as well. Right now, you can ignore it. You can even have recursion. Like you compute something at the output, you pass it again as an input, right? This is what happens in recurrent neural networks, right? Now, what we start with do not have those weird connections, but we gradually learn that we need to add them as well, and then you're going to see that they are having benefits. They make things complicated, but they're going to give you more power. Okay? Great. Now, if you have a layer neural network, then in this neural network, you have 3 different kind of layers. You have input layer, right? The input layer is collecting a bunch of your inputs, right? Everything inside the input layer is not a neuron, right? It's simply your input. So here you have x1 till xn. If it's an image, is the value of the pixels, right? This is the input layer. You have one output layer. This is the point, the last layer, which is computing everything for you, right? It's giving you the output that you want, right? And of course, this guy is collecting a bunch of neurons, right? And anything in between, this is what we call it hidden layer. And the hidden layer is simply because if you look from input or output, it's hidden from your eyes, right? There's something happening inside that you don't see it. Everybody's cool? Questions? No question? Now, let's look at this hidden layer. What is the depth, this layered architecture? What is the depth of this layered architecture? If you think of this one as 3, like you assume you have really these 3 different layers, right? So this is the first one, second one, third one. How many hidden layers you have? 2. You have 1 output layer and 1 input layer, right? So you can always say that the depth of a layered neural network is actually the number of hidden layers that you have plus 1. Everybody's cool? Yes? Sorry, I didn't get you.
How does the cycle in the graph affect your definition for the depth?
It does not impact it.
Doesn't? So what would be like the depth of, I guess you just...
That is depth, I mean, that's going to be a bit tricky. This is going to be depth in time, which could be very deep. That's correct, right? But we're not talking about that yet. Because here, you potentially give your input, you do all the computation, it's over. This is one time instant, right? And then that recursion is going to happen the next time instant, right? So that means that still you need to wait as much as depth to see your first output, right? And then new output is going to get impacted. That's correct. Okay, everybody's cool? The depth is the number of hidden layers plus 1. So we said that a deep neural network is a neural network which has depth more than 2, right? So if you wanted to interpret it in terms of the number of hidden layers, how you can define a deep neural network? A deep neural network is a network which has how many hidden layers? More than 1 hidden layer. If it has 1 hidden layer, it's not deep. If it has more than 1 hidden layer, that is deep, right? So the first guy is what we call a shallow neural network if it just has 1 hidden layer. But if you have multiple hidden layers, then this is a deep hidden layer. A deep neural network, sorry. Now, you might say, what is the twist here? What is the twist between 1 and then anything more than 1? Well, if you check assignment 1, then you're going to see why this is the reason. Because initially, based on the universal approximation theorem, people said that Well, if I have a neural network, I just need one hidden layer. And I need to make this hidden layer very, very, very large, then this is going to do the job for me, right? But then people started to see, out of this property of cascading different layers, you can simply show that if you can, for example, approximate 10 functions using one hidden layer with, I don't know, 10 neurons. If you take those 10 neurons and you put it in a cascaded form, like you make more hidden layers, 2 hidden layers, 5, then the number of possible functions you can approximate is going to increase exponentially. So it's not 10 anymore, it's 10 to the power 2, 100, right? And then they said, okay, if I have enough number of hidden layers, say 5, 6, 10, right? 10 hidden layers, then I am just increasing the number of possible functions exponentially with exponent 10, right? And this means that I can pretty much explain any represent any function, right? So that was the twist. The people somehow started from thinking about one single hidden layer, which was the conventional neural network thinking, into adding multiple layers. And this is why people started to call that deep, right? So you are just following this idea of going deep, more than one hidden layer, right? And this is where the term deep comes from. Now, if you solve the first assignment, as I said, you're going to see this property of the exponential increase in the capacity in terms of depth. Okay. Rather than that, any question on this? Everybody's cool? Questions? No questions? Great. So now, if we look at this neural network that we had before, we have here 3 different perceptrons. 2 of them just build the first hidden layer. The last one is just building the output layer. The input are x1, x2. The activation function here is simply the step function. Is it a deep neural network or not? Is it? No, it has just one single hidden layer. It's not a deep neural network, obviously, right? So it's a shallow neural network. Questions? Great. So if you got no question, now we do know what is neural network. And that neural network is again a model for us because it has one input, it has one output, and then it does a bunch of computations in between. And these computations depend on parameters, right? The weights and the biases of those neurons inside, right? Now, you can play with these weights and biases such that this connection between input and output is what you want, right? So this is a model, and if you tune those parameters, you are basically doing training, right? So it's the same thing as before. So you have a deep neural network, and deep neural network is just simply a parameterized function. Now, this deep model, this deep neural network, could have a bunch of hyperparameters. Now, if I talk about hyperparameters, it is something more similar to what you have heard before, right? For example, how many layers you want to put, right? How many neurons you want to put in every layer. These are hyperparameters. But again, as we discussed before, these are the things that you need to specify before you can draw your neural network, right? So you need to first specify your architecture. I want to have 2 hidden layers. Every single of them has 5 different neurons. 1 output layer with 1 single neuron. I want to have ReLU activation for all of them. I want to connect everything to everything, right? That is what you choose. These are all hyperparameters. But once you fix that, then you have a bunch of weights and biases that you need to learn. These are all learnable parameters, right? And you can count the number of learnable parameters inside your neural network if you do exactly know what are the hyperparameters, right? So that's about this. And, well, this, if we have any architecture, as I said, you can, when you fix the hyperparameters, you can basically count the number of learnable parameters. And we can, as an example, look at this guy, right? Let's look at this guy. In this guy, I have specified the hyperparameters. What are the hyperparameters? For example, I said I want to have 4 different neurons. 1 of them is at the output. 3 of them are in between, and they are connected in this form. And I have specified the activation for every single of them. This is hyperparameter. But once I fix the hyperparameter, now you can count the number of weights and biases that you have here, number of parameters. Can we do this? Let's look at the first guy. For example, look at neuron 1, 2, 3, these 3 neurons, right? How many inputs they get? Every single of them gets 2 inputs, right? Now, if you have 2 inputs in a neuron, how many parameters you have? 3, right? Every input has its own weight. You have a bias, right? So you have 3 neurons. All of them have 3 parameters, right? 2 weights and 1 bias. So these guys together, they have 9 different parameters. What about the last guy? How many inputs it takes? 4. How many parameters it has? 5. So what is the total number of parameters in this model? 9 plus 5 is 14, right? So in total, you have 14 possible learnable parameters in this, right? They are the weights and biases of this architecture, right? And you can extend this idea to giant neural networks, right? All of them are the same. Questions? No question? Okay. So if you got no question, let me just go for the last slide, I guess. And that is, I want to get back to the definition of deep learning. This is the definition we started this chapter with. So we wanted to understand what is deep learning. And I told you deep learning is a subset of machine learning where you are going to accomplish a learning task by using a deep neural network, right? Right now, you do know what is machine learning, what is a neural network, what is a deep neural network, and what is a learning task, right? Basically, you want to do that function approximation. As a model, you use a neural network. And if you set that neural network to be deep, it means that it has more than one hidden layer, then you are doing deep neural network, right? So this means that deep learning is basically a branch of machine learning where when you want to accomplish a task, when you want to learn the connection between input and output, you're going to put one